Okay, good afternoon. And today we're going to continue talking about the solution of differential equations. Especially, we're going to talk about high order differential equations briefly. And then we're going to talk about the connection between high order differential equations and actually first order differential equations. Before that, we first do a warm-up problem. The problem is to write down the form of a particular solution to several equations. The first one is this. Let's wait for 30 seconds for you to think about, and then we're going to work it out together. Okay, so as we talked about last time, the first step is always to look at the auxiliary equation. The right-hand side, especially this exponent here, we look at the relation between this exponent and the root of the auxiliary equation. So this is 2y, 2r minus 3 equal to 0. So we solve and find that this is r1 equal to minus 3 and r2 equals to 1. So this minus 3 is exactly the same as here in the exponent. So we know that the solution should be t times, first of all, we need a t here. Inside, we do this method of undetermined coefficients. So this is L equal to 0. There's a t to the L equal to 0. So inside, we only need a constant term here. So exponential minus 3t. Any question? Okay, second problem.
Sorry, really quick. Why is it t instead of t squared? Because you have two roots. So
Yep.
isn't
The question is why t instead of t squared? So we multiply t squared only if this minus 3 is actually a double root. So,
but isn't there two root, r1 and r2?
yeah, but this one is a single root. It's a simple root. So its multiplicity is 1. So if you always have two roots, right? So I mean, they're either distinct roots or they're repeated roots. Here it's not a repeated root, so you only multiply by t.
Oh, so what do you mean is there's a duplicate of -3 because the solution of r1 equals -3 and then e is to the -3 power. So those two duplicate, so you only have one root? Is that?
So this exponent only agrees with one root, and this is a simple root. So if you look at the lecture notes from the previous class, you'll find that if this problem gives you the r squared, let's say, plus, so this is r1 plus 3 squared, and then you will have t squared. So if the auxiliary equation looks like this one, then minus 3 is called a double root. Correspondingly, we're talking about, so we're talking about 3. If the equation look like this, then yes, you need a t squared. But here, it is only a simple root because these two roots are not the same.
Okay, so basically if the solution to the r has like two distinct values, then it's a single root. But if they're like the same solution but multiplicity of 2, then it's a double root.
That's right.
Okay, thank you.
Any other question? Okay, so then you have, let's consider this problem. So this is very similar, especially the auxiliary equation is exactly the same thing. Here, exponent here is 1, which agrees with this 1 here. So then ypt, we know that this should be again multiply t. Again, this is a simple root or a single root, and this is a2 inside. This is t squared. Although there's only t squared, the lower order terms are also needed because when we solve the linear system, we don't know whether these things vanishes or not. Maybe they vanish, but maybe they not. They don't vanish, and therefore you have t times method of undetermined, this undetermined coefficients, a2, a1, a0 times the exponential t. Any question? Third one, still the same thing, but equal to cosine t. So for this one, we always need to think in terms of Euler formula, which means that this is, I write it to be 1/2 1 plus I t 1 minus I t. So these things, either 1 plus I or 1 minus I, they do not agree with -3 or 1. So we know that so 1 plus minus I is not a root. Therefore, I can make a guess, ypt, and this is a naught exponential 1 plus I t, b naught psi t here, a naught, b naught. They are complex numbers. This is entirely equivalent to the following assumption: c naught cosine t, cosine t, d naught sine t. Again, although sine didn't appear here, there is only cosine, but with the linear combination of these two terms, it will naturally generate a sine. Here, this is real, this is real. We expect that the two constant to be determined by the initial condition, to be determined by matching with the left-hand side, they are real. So this, either this one or this one would be a valid ansatz. Any question? Fourth one, y double prime plus y t cosine t. So again, we look at the auxiliary equation, r squared plus 1 equal to 0. This is r equals to plus minus I. Now let's see. So let me look at the right hand side. T cosine t equals to 1/2 t exponential it and plus 1/2 t exponential minus it. So we found that this one corresponds to plus I, this one corresponds to minus I, and both of them, I mean, I can handle these two terms separately via the principle of superposition. Each of this I or minus I is a single root. So ypt is t. Let me just write down the real version, c1t plus c0 cosine t plus again t d1t plus d0 sine t, here c0 c1 d0 d1, they are real numbers. This one is slightly more complicated, which summarizes the previous cases, which covers all the previous cases. I want to make sure that you understand. Any question? Okay, So now let me now talk about the generalization to high order differential equations. So the basic message is that they're the same as, almost the same as second order. It's discussed in the chapter 6, but we pretty much skipped that chapter where, as you can see from the syllabus, we'll directly go to the chapter 9. So this is really relatively brief discussion, and so that you will know that generalization to higher order differential equations is really straightforward. Let's start with the example. Solve the following initial value problem. So y triple prime minus y prime equals to t plus sine 2t. It's quite general, and start with 0 equal to 2, prime 0, 0. Now it's a third order differential equation, so I also need to specify the second order derivative of the initial value. So this is an inhomogeneous differential equation. So 0, we have step 1. We need to look at the homogeneous part, which is find the general solution to this problem equal to 0. Now we know we need to write down the auxiliary equation, which is r cubed minus r equal to 0. And we can factorize it. We find this is first root is 0, second root is 1, because this is r times r squared minus 1. Third root is minus 1. Why do we care about such factorization? Is because if we write the left-hand side to be ty equal to 0, then ty with this factorization, remember that ddt and identity, they commute. So this will be minus r1i ddt minus r2i ddt minus r3i. So if r1, r2, r3, they are distinct solutions, distinct roots, then I can, they all commute. So I can just put any of those on the right and solve a first order differential equation. I get a different solution for each root. Then they're all linearly independent. Then we're done. Indeed, here the basis of the null space of T is, this is 0, and exponential 0t is a constant, so the basis is 1. This one, the basis is exponential t. This one is minus t. Any question?
Could you explain the minus r1i and the minus r2i and r3i?
So let's see. So this is exactly the same thing as the second order differential equation. Forget about R3. There we factorized the second order differential operator using the two roots of the auxiliary equation. Now I just factorize the third order differential equation using the three roots of the auxiliary equation. So that when you multiply them together, let's say the leading term, that's like the third order derivative. Similarly, it will be second order derivative here. It doesn't have any first order derivative coefficients -1 and a constant term, which is 0. Did that answer your question?
Yeah, so it's similar to like factoring
it's exactly the same thing. And here, of course, unlike the second order differential algebraic equation, you always know the solution. Third order thing, there is a closed form solution, but it can be pretty complicated. Here, I only talk about this algebraic equations, which are easy to factorize. Here, you can directly see what the roots are. Did that answer your question?
Yeah, thank you.
So any other question? Then we talk about step 2. So step 2 is the following. We need to find a particular solution. To find the particular solution, we need to use superposition principle. Let's look at the right-hand side, which consists of 2 terms. One's t, one's sine 2t. So we separated them into 2 problems. One is minus y prime equal to t. I mean, I make this problem deliberately complicated so that to cover all the aspects you have seen before. And you understand this problem, you just have understood the entire procedure of working with high order differential equations with constant coefficients. So we need to make some guesswork again. But now, based on the knowledge of solving second order differential equations, you can make really educated, you should be able to really make an educated guess. So t is, I mean, this one, t is the same as 0 times t, right? And 0 is a single root of the auxiliary equation. The 3 roots are 0, 1, minus 1. So 0 is a single root. So presumably, when I multiply, it should take the form a1t plus a0. Right? Okay, so let us now try to work it out. So this is a second order derivative. So second order, this is a polynomial of degree 2. So the third order derivative would vanish. First one is 1, this is 2, a1t, and this is plus a0. Second order derivative is 2a1. Third order derivative just vanishes. So this means 2 minus 2a1t minus a0 equals t. a0 is 0. a1 is minus 1/2. So I solved for this first sub problem. ypt is minus 1/2 t squared. Any question? Okay. Second sub problem. This one equal to sine t. Once I obtain the 2 of them, I put them together, I've solved the problem. So y minus y prime equal to sine 2t. Now, again, I use Euler formula. So this is 1 over 2i exponential 2it minus yt. Just like we were expanding the cosine in terms of the real parts of the exponential function, and we expand sine using the imaginary part of the exponential function. So this is cosine plus I sine, cosine minus I sine, minus minus. They cancel, divided by 2i, you directly get sine 2t.
Why do we need the 1 over 2i?
It's just 1 over 2 times I. So this is an identity, and you can check.
Okay.
Yeah, you just do the Euler formula. You will find that the real part is the cosine. They just cancel. The imaginary part, they will have a 2i in front, and therefore you divide by that 2i. So this is very much analogous to, maybe you're more familiar with this now, and this is just the imaginary part. They're equally useful. Okay, so now I know that this is 2i, not a root. This is not a root of cube minus I equal to 0. So I can make a guess. Right now, again, educated guess, A naught cosine 2t plus B naught sine 2t. Here, A naught, B naught, yeah, real numbers. We can also do the exponentiated form with A naught, B naught being the complex thing, as we talked about for a few times. They are completely equivalent. Now I just evaluate yp prime t. So this one is minus 2 A naught, and this is sine 2t, 2 B naught cosine 2t. It's quite mechanical. So keep doing, minus 4 A naught cosine 2t minus 2 B naught 4 sine 2t. Keep doing t, and this is 8 A naught sine 2t, and this is minus 8 B naught cosine 2t. I'm just doing the computation. Any question? Okay, so now we have typ. First, there is the cube term. This is 8 minus y prime. Let's collect. So this is 10 A naught sine 2t, and minus 10 B naught cosine 2t equal to sine 2t. So we have A naught is 1 over 10, B naught is 0. So ypt is 1 over 10 cosine 2t. Any question?
I might have lost you from y triple prime to t ypt.
Okay. So
From how do you get the minus plus 2 minus 2?
Minus 2? I just take a derivative.
Like,
so
no, but like from y triple prime pt, how
yeah.
did you get from there to t p
yp?
ty? Yeah.
typ is just a y triple prime minus y prime, right?
Oh, I see. All right. Okay. Thank you.
Yeah. So any other question? Yeah, I know it's a long procedure. As I said, I deliberately choose this problem to cover almost all the cases we have seen. So you see this entire thing. Okay, so we're almost there. We found a particular solution. We found the general solution set to the homogeneous equation. Plug in, third one is to plug in initial value. So the general form is, so this is what, so this is the first one is minus 1/2 t squared, minus 1/2 t squared, 1 over 10 cosine 2t. C1 times exponential to the 0 is a constant. C2 t, C3 minus t. So now you just match the initial condition. So this is 0, this is 1 over 10 plus C1 plus C2 plus C3. This is 2. And y prime 0 is prime 0. This is 0. Prime, you get a sign that's a 0. And then I have a C. C1 prime is a 0. This one, C2 minus C3 is 0. While double prime, that's also 0. Double prime here, it is double prime here is minus 1/2. This one double prime is what is first I have a minus 1 over 5. So this is I think that's sorry. So first of all, I have a 1 over 10, so minus 2 sine 2t. I take another one, so it's a minus 4. So this is cosine 2t. Take a cosine t equals to 0, so that is 1. So this is minus 2 over 5. Right. So then this one is plus c2 plus c3 is 0. Now we go back to chapter 1. As you see, throughout this entire semester, we're only 2 weeks away from the end of it. Throughout this entire semester, in the end, no matter what you're doing, you will end up with a linear equation that goes back to chapter 1. Now you're all experts of doing that. I will solve that here. I got the solution. I think this is 7 over 10. This is 7 over 10. And you plug it in, we solved the entire problem. Any questions? Okay, so now you see I've solved the third order differential equations. I can talk about now nth order differential equations, constant coefficient, which is y to the n. Here, parenthesis n means the nth order derivative, a1, n minus 1, all the way to a, let's see, a n minus 1, y1, plus a n y equal to 0. So how do I solve this? I first do the auxiliary equation. So the left-hand side would be ty, and again the ddt and identity they commute. So this is a1 n minus 1, an equal to 0. So this is the nth order algebraic equation. We want to find the root of that. We briefly talked about fundamental theorem of algebra before. You don't need to know the proof of it. You just need to know for any nth order algebraic equation, there are always n roots, counting multiplicity. So if there's a root 1, there's another root 1, counts twice. Multiplicity in C means that they're in the complex plane. So let's say r squared plus 1 equals to 0. There's no real root, but there are 2 roots in the complex plane. One is plus I, one is minus I. Of course, this is easy to say and difficult to do, especially if you ask you to solve a 5th order polynomial and find the roots of that. And I mean, there's no general formula to do it. So definitely the factorization will not be a bottleneck in your homework or exams. This is not about whether you're clever using Mathematica or something to solve a 6th order differential equation, but the principle is exactly the same. Now, let's say you want to know the general solution to this homogeneous equation. Now we ask whether, let's say R is a root, is a single root or a simple root. So I know that exponential RT is a solution. What if you have a complex pair, beta, you have another root minus I beta, so complex conjugate pairs. Indeed, because all the coefficients are real, if there's R1, that is a root, I can just take a bar over the entire equation. You find R bar is the equation, which is exactly alpha minus I beta. So if one appears, the other must appear. Then I consider the span of this and this. This span means that I'm doing linear combination with a constant coefficient. So this is exactly the same as the span of alpha t cosine beta t sine beta t. You see, it's exactly the same as the second order thing. So this is the second case. The new case is that R is a repeated root of multiplicity k. What it means is that t, so this polynomial, this is the polynomial of interest, is factorized into, let me use this R naught, because otherwise I cannot write R naught. Oops. R naught kth power times another polynomial R, such that G R naught is not zero. So that R naught, this is what it means that it is a polynomial root of multiplicity k. Any question? So in the case of the second order differential equation, we need to worry about k equal to 2, but since it's only a second order polynomial, GR must be constant without loss of generality. We think this is 1. So in the second order case, we know that it takes the form of the span exponential R naught t, t times exponential R naught t. Now, if we're talking about the kth order derivative, naturally, this is, I just generalize to t to the k minus 1 times exponential RT. Why is this the case? So recall that, how do we generalize this to the recall second order? One way to see how this t arises is you have two roots, but they're very, very close to each other. So this is R naught plus epsilon. Epsilon is a very, very small number. So if the roots, one is R naught, one is R naught plus epsilon, then indeed this is the span. But since we're dealing with the span, we can do arbitrary linear combination. I can arbitrarily add two things together. I can also subtract them. I can divide by a constant, let's say epsilon. And this one, I take a limit, epsilon goes to 0. So this one is just the derivative. That is, so this is t exponential R naught t. Any question? Now look at the third order. You understand the third order, you understand the nth order. Third order, we do the same thing. Assume there are three roots. I don't think they are R naught, but actually they are R naught plus epsilon t. The other is R naught plus 2 epsilon t. Okay. And now I take epsilon equal to 0, then I have a root of multiplicity 3. So I can play the same game the goal, there are two goals. One is that when I take a limit, this is well defined. And the second is, yeah, any question?
The question that I have is when epsilon it goes to 0, so just like a little bit above on your note, shouldn't the span be e to the power of r0t, comma 1 over t, since the e2's will get canceled out?
Sorry, 1 over t? Why 1 over t?
Because like since when e is equal to 0,
Yeah.
like wouldn't it be r equal to the power of r0 times t minus e to the r0 t over t? So basically, like
No, it's multiplied.
exponentials will cancel out.
Is multiply t. So this is just the chain rule. Like you can always think about that is you multiply t here, you multiply t here. You see, so this is exponential r0 t plus a small constant called the epsilon t. I redefined that.
Oh, wait, that's an epsilon, right? Ah, okay. Sorry.
Actually, that's
Oh,
not.
I thought it was a t. Okay.
Sorry. So let me write it in there. Epsilon. Okay. Is it good?
Yeah.
Okay. So yeah, just realized that they look a little bit similar. Let's do that. So now I have two goals. One is I take when I take epsilon go to 0, they should have a well-defined limit. It shouldn't be something's blowing up. And two is I should originally this is a space of dimension 3. It should still be a space of dimension 3. The first one we play this game, as you have seen before, t minus rt. Note that the second one we cannot play the same game, because let's see that if we play 2 epsilon, so this is 2 epsilon t minus r0 t. So this one, if I take the limit epsilon go to 0, this is r0 t. This is chain rule r0 t. This is again t times r0 t. So the 2 epsilon just cancel here. So this one, I got 2 linearly dependent solution. So this doesn't not work. How to make it work? The way to do it is instead of this one, we make a different linear combination. So what we do is fix. Fix is the third one should be exponential r0 t. And I here is times, there's a epsilon square. So this is, yeah, okay. Let me write it in this way. So this is, so this is r0 plus 2 epsilon t, and this is minus 2 plus epsilon t plus epsilon r0 t. Now I do a Taylor expansion. I do a Taylor expansion when epsilon go to 0, and this one will give me, so let's see. So this is, first of all, I do, let's see, I can expand, I can do this. So this is r0 plus epsilon t, and this is exponential t epsilon square t square, and this one is this is minus that minus epsilon t epsilon square t square minus 2, and then there is all the epsilon cube term going on. Epsilon cube will cancel with this epsilon square. There's an epsilon term going on. So now take epsilon go to 0. I found that 1, 1, 2 cancels. This one cancels. I only leave with this term. Epsilon squared was canceled here, and therefore I have t squared times exponential r0 t. So indeed, the span, if you have the third root, r0 t t, and the third one is t squared exponential r0 t. Again, this kind of derivation is only for you who are familiar with this procedure. I think after calculus 1a, calculus 1b, you should be familiar with this, but this is more for you to understand the derivation. Any question?
Could you please explain how you're able to factor out e to the r naught plus epsilon t?
Because these are scalars, so then this just becomes a plus b. The answer? Because you factorize that out, you have an exponential epsilon t. This is 2, and this minus 2. This is exponential minus epsilon t.
Okay, thank you.
Any other question? Okay, so this is yeah. So let's look at another example. Okay, before we move on, we want to solve y to the 4th power minus y to the 2nd power equal to 0. How do we do this? So the auxiliary equation is r to the 4 minus r squared equal to 0. This means r squared minus 1. So this is plus 1 minus 1. So if you're asked to ever to solve such an equation, it will be the bottleneck will not be the auxiliary equation. It should be very easy to factorize. So then you have 1, you have a r1 is 0. So this one has multiplicity 2. R2 is 0. This is multiplicity 1. 1. So then I just have yt equal to c1 plus c2t. That comes from here. Then I have c3 t plus c4 minus t.
Professor, does that say multiplicity minus 1?
Oh, sorry. Thank you. And any other question?
Can you briefly say which C1 corresponds to which root again, or which C corresponds to which root when you write out all 4 C, like all 4 terms?
Sure. So C1, C2 corresponds to this one. So let me use change the color to make it clearer. So I have a C1. This one corresponds to 0. So this one, C3, corresponds to 1 because this is exponential. This is 1. And then finally, I have minus 1. And this is C4.
Perfect. Thank you so much. That makes it much clearer.
Okay. Very good. So now I'm gonna, okay, so I probably don't have enough time to cover. Just to give you a preview of the next lecture. Now you have seen how to solve the high order differential equations. It is perhaps surprising to hear that all high order differential equations are first order differential equations. Okay, so this is actually sounds unbelievable, but it's actually a very, very simple construction. Let me say briefly using the example I just had to show you how this works. So they are not first order scalar differential equations, but they are vector differential equations. So I define y vector t to be the following, to be y1t, y2t, y3t, y4t. This is doing nothing. Their respective definitions are yt, it's the y here, y prime t, y double prime t, y triple prime t. Okay, so I just list all the derivative up to the highest order, and not including that, the highest order. Now I consider d dt yt. Then this one, the first one becomes y prime t. Second one becomes y double prime t. Third one becomes y triple prime t. And finally becomes y to the 4t. Any question? So what am I doing here? Now I do a matrix vector. I write it in the form of a matrix vector multiplication. So this is the following. Remember, this is y1t, y2t, y3t, y4t. So y1 prime equal to y2. So this is 0, 1, 0, 0. Is that clear? Okay. y2 prime equals to y3, 0, 0, 1, 0. y3 prime equal to y4, 0, 0, 0, 1. You see, I haven't used the equation yet. This doesn't make sense. Finally, y4 prime equal to, using the equation, equal to y2. So this one is the information of the equation. This is nothing but a constant matrix A, which is A times yt. Indeed, we got d dt yt equals A times yt. So I've converted to a first order equation. So this is called the normal form of this high order differential equation. You might say, how come this is normal? This is abnormal, but actually this is called the normal form. And when you, especially on modern computers, if you want to use a computer to solve a differential equation, the first step you do is to convert that into this normal form. And we're going to talk about this on Wednesday. Any question?
Can you go over why y4 prime is